Uh, Hello everyone, and welcome back to my new video. In this video, I am going to continue my discussion on the topic of black hole. And in the last video, I had discussed about spaghettification, and I had discussed that when we try to approach near the black hole, we experience a very strong gravitational force. So in this video, I am going to tell you that why I said in my last video that when you approach near the black hole, you will going to experience a very strong gravitational force. So what is the reason behind this? We are going to find out the why behind this. And in this video, we are going to find the reason. We are going to do logical analysis of everything that we are going to study. And even in my upcoming videos, I will not just teach the facts, but also I will try to give the logical analysis, the proofs of everything which I teach, which I speak from my mouth. Everything should be proved. So physics is not just about memorizing facts, it is about the logical analysis. You should be able to relate it with your common sense. So yeah, now come back to the our topic. So uh, for proving this, we need to have a basic and clear cut understanding of a formula that we use in the gravitational force. So how we calculate our gravitational force? We calculate our gravitational force by using a formula, and the value we get from the formula is capital F equal to capital G into capital M into small m by r square. This is the formula of gravitational force. So here the capital G is the universal gravitational constant, and the value of capital G will remain constant everywhere. That means the value of capital G on Mercury, on Venus, on Earth, on Mars, on every other planet or solar system, the value of capital G will always remain constant. That will always remain same. And this capital M represents the mass of planet. Capital M is mass of planet, and the mass of planet will change for every planet because not every planet has the same mass. So yeah, and this small m is the mass of object. This small m is the mass of object, and this small r, suppose it's a planet. Suppose this is a planet, and this is the center of the planet. So this distance, the distance from the center of planet to the surface of planet, this distance is called a small r. So now that you have got the basic understanding of this formula, we can derive the region that I discussed. We can derive the region, we can derive the logic behind this. So let's make this our equation 1, and we also have another equation. And as we have studied in class 9, F equal to ma. From this formula we can calculate the force. So here the value of a, this a represents acceleration. This a represents acceleration, but in the case of gravity we can replace this small a with a small g. And what is this small g? This small g is acceleration due to gravity. This small g is acceleration due to gravity. And the value of a small g is different on every planet. Like let's say on moon, the value of a small g is 1.6 meter per second square. On the Jupiter it is 24.7 meter per second square. And yeah, from this you can draw a conclusion like this. Value of a small g on Jupiter is 24.7 meter per second square, and here it is very small. That means on the Jupiter you will feel that your body is very heavy. You will feel the body is very heavy on Jupiter, but you will feel that your body is very lighter on this moon, because the acceleration due to gravity on moon is very less, that is 1.6 meter per second square. But on the other hand, on the Jupiter, the value of a small g is a very large value as compared to this value. That is the reason you will feel like your body is very heavier on this planet. And talking about earth, as we all know, the value of acceleration due to gravity on the earth is 9.8 meter per second square. And sometimes we round off to this to the near value, and we write the value of acceleration due to gravity on earth is 10 meter per second square. For making our calculation easier, we use the approx value. So yeah, so now we have that got the basic understanding of this formula, and we have got a basic understanding of this small g value, that is acceleration due to gravity. So now just try to make the things very simple and try to equate these two equations. So our first equation is this, and our second equation is F equal to mg. We wrote first F equal to ma, but we have replaced a with a small g, because in the case of gravitation we can replace this small a with a small g. So our formula becomes F equal to mg. So this is our equation 2 and this is our equation 1. Here on the left hand side we have force equal to this, on and in this formula we have in this formula we have force equal to mg. So we can equate these two equations. So now when we equate these two equations, we get mg equal to gm m by r square. So now as you can see, this small m is similar on this both sides, so we can cancel out this small m from both sides. So now the value of g becomes capital G into capital M by r square. So look at this formula. The value of acceleration due to gravity is capital G into capital M by r square. Look at this formula. Take a deep breath and wait for a second, and try to visualize it in your mind that what conclusion you can draw from this formula. Before I speak anything on this, I want to comment anything. I want you to think from your end, because I want the curiosity to develop in your minds, because without curiosity there is no point in reading, in just memorizing facts. If you are not curious about things, about concepts, there is no purpose of educating yourself. So yeah, wait for a moment, take a deep breath and try to visualize this formula, try to make some conclusion out of it, then I will continue from here. So yeah, let's now continue. As you can see in this formula, there is no small m. Nowhere on any side you can find small m. That means the value of small g, that means the value of small g is not dependent on a small m. What is small m? Small m is the mass of object. So we can conclude that acceleration due to gravity is not dependent on the mass of object. So now we will now going to look at this formula from the perspective of black hole. And when we look at this formula from the perspective of black hole, so I am writing this formula again here, G equal to gm by r square. So when we look this formula from the perspective of black hole, this capital G is 6.67 into 10 to the power minus 11 Newton meter square per kg square. This will always remain same. Even in the case of black hole, this value is always remain same. This value will always remain same. And this capital M here will remain the value of mass of black hole. This will represent the mass of black hole. And as we know, how the black hole was formed. Black hole was formed from a star that was almost around 20 times larger than the size of sun. When this star died, when this star died, because inside the star the hydrogen that was getting converted to helium, this fuel got exhausted, and this when this fuel was finished, the star died, and when the star died, it got compressed into a very small size. So now the star is now compressed to a very small size, but the mass is still almost the same. There is no significant difference in the mass. That means the value of r is changed now. When the star was alive, the value of r, that was the distance from the center of the star to the surface, this was the small r. The small r was a large value when the star was alive, but when the star died, this was converted into a black hole. This star was converted into a black hole, and now the size of a star is now very small. This black hole is very small, and this r value is very small. So I am repeating everything that I said. I was saying that when the star was alive, when the star, that was a very huge star, almost 20 times the size of sun, when that star was alive, that time the value of r was a very large value because the star was very large. But when the star died, when the hydrogen that was being converted to a helium, when that fuel got exhausted, then the star died. And when the star died, this star get converted to a black hole, and it was compressed to a very small size. This star got converted to a black hole, and it was compressed into a very small size, and this r value now is very small. If you can't relate it, thus just consider a scenario. Suppose this is a car. You have a car. That car is a very huge car, and you applied somehow, you just tried to compress it by applying a very large amount of force. And when you applied a very large amount of force, this car was compressed and it became a very small car. This very small car is a toy car from which our children play. This car is now converted to a very small car, but only the size is getting decreased. The mass is still almost the same. Mass is still almost the same. There is no significant difference in the mass. Mass is still the same, but the size is getting decreased. And the same thing happens in the case of stars. When the star, that was a very huge star, when the star died, it get converted to a black hole, but the mass was still almost the same, only the size was getting decreased. And when the size was getting decreased, that means the value of r, that was the distance from the center to the surface, it is also decreased. R is also decreased. So in this formula, this mass, this capital M value, is a very large value. That was the mass of the black hole, but this r value is now a very small value as compared to numerator. The numerator is a very large value, and this denominator is a very small value. And this is a basic mathematics, that when we divide a very large value with a very small value, we get a resultant that is a very large value. That means the value of a small g is a very large value. In the case of black hole, in the case of black hole, we get the value of a small g, that is a very large value. That means the acceleration due to gravity in the black hole is a very large value. G in the case of black hole is a very large value. G in the case of black hole is a very large value. That means, as I had discussed in the last video, this is a black hole, when you approach near this black hole, and because the value of a g, the value of a small g, that is acceleration due to gravity on the black hole, is a very large value, there you will feel a very strong gravitational force near this black hole. And once you enter this event horizon, this is the event horizon, the point of no return. When you enter this point of no return, when you enter this event horizon, there is absolutely no chance of coming back due to the very strong gravitational force that you experience on this black hole. So now, using our formula, we have concluded, we have proved that why I said that near the black hole you will experience a very strong gravitational force. So we have discussed these things. We have also discussed from our concepts, from our theory, and we have derived it from our formulas as well. So now I hope you have got a clear-cut understanding of these things, and I am very grateful that you have watched this video till here. And still, if there is any doubt, I am always ready to make another video, and this playlist will continue in my upcoming days. uh, so yeah, thank you very much.